Let's go.
Your simple is not that simple.
284.
284, huh?
Yeah.
What section's that from?
I'm sorry. 1.5, section 1.5.
Oh, okay.
Conic sections. It says the following exercise considered the following polar equation of conics, determine the eccentricity and identify the conic.
Consider the following okay. Determine the eccentricity and identify the conic. Okay. Right. So this is a conic section. This is the part that I told you I won't be holding you to.
Oh.
All right. I'll just mention it just for kicks, but I won't be asking a question like this, although I probably should since we just finished talking about polar coordinates, right? I talked about in rectangular coordinates, right? We talked at length about how to express ellipses, parabolas, hyperbolas in rectangular coordinates, but I didn't talk at all about how to express them in polar coordinates, right?
Mm-hmm.
But yeah, but if you happen to look through the book, you'd see that I'll transcribe this so I can look it up in the book. R equals 3 over 4
-4, so.
negative 4 plus 3 sine theta. And if you scan through somewhere in here, right about, probably in a book, has like a box in it. Oh, look at that, there it is. Polar equation of the conic section. The polar equation of the conic section with focal parameter P is given by this. It can appear in one of two different forms, with a sine or a cosine.
Right.
Right? But as you can see how, if you compare this and this, it's not a perfect match because in both these cases there's a 1 plus or minus something. Right? So in order to identify what type of a conic it is, I'd want to be able to put it into that form. And how would you do that? I have to somehow make this -4 into a +1.
So if you take out the negative.
Yeah. How about I do this? I'll think of it like this. I'll factor out a -1/4, huh? So that's going to end up being a 1 minus 3/4 sine theta. Is that right?
Cool.
You can double check it. If I distribute the -4, that would be a -4, and that would be a +3, right? So, and to make it look like one of those, now it's a 1 plus or minus something times sine. It's starting to look a lot like this one.
So then, question.
Uh-huh.
So I don't feel like that. So the e's are the same.
Yeah. Yeah.
So it's 3/4 times e equals 3.
Rather, I would say 3/4 is e.
But to get the 3 down.
Oh, I see what you're saying. So I'll just write this as -1/4 times 3 is the top.
Right.
And so, based on what I see right here, I can see that this is E. E is 3/4. And since this right here is EP, I can then see that since EP equals -3/4, and since E actually is 3/4, I can then see that P is -1. Right? And P is the distance to the focus. Right?
Hold on.
We talked about that in the context of a parabola.
But so EP
Mm-hmm.
But wouldn't EP have to equal 3? Because if it is EP and the top is 3,
Well, the top isn't 3 though. See that factor I pulled out?
so it has to be factored to the top.
Yeah, because notice how in this form, there's no factors in front of the fraction.
Right. So 1/4 of 3 is 13/4.
Mhm.
No. Oh, okay.
Mhm.
I think. Yeah.
Yeah. It's like multiplying fractions,
Oh, yeah.
3/4. Yeah. And furthermore, we talked about this, if the eccentricity is 3/4, that puts it between 0 and 1. And in that case, we would identify the conic section to be a...
Hold on. I know this one. I actually do know this one. It is the. Hold on. Oh, yes, ellipse.
Yep, that's right. If you're looking in the book, I think it looks like it's right above. Oh, yeah.
Oh, yeah, there you go.
See
That's
that? So because of this, I can clearly see that this is an ellipse, right? Furthermore, the distance that from the vertex or the edge of the ellipse to the focus is 1. Because P is, right, the focal parameter, right?
Okay.
Let me double check that.
So then the directrix
Mm-hmm.
would be
Right.
4/3? No.
So the directrix, so we also talked about how the eccentricity, right,
Uh-huh.
is C over A.
No,
Is that right?
But that was the a squared plus c squared of an ellipse. A squared plus c squared equals b squared.
Uh-huh. Right. So the eccentricity of a conic section is defined to be the distance from any point on the conic section to its focus, divided by the perpendicular distance from that point to the nearest directrix. The value is constant for any conic section, and can define the conic section as well. So, yeah, so here we have the ellipse, and yeah. So, yeah, so okay, so let's see here. So for this one, so the ellipse that we're gonna get is gonna look something like, I don't know, something like this. I'm not sure about the orientation yet. Right. But I can see that if, from this point to the focus, there's actually 2 foci, right?
Right.
F1 and F2, let's say. But it's symmetric. So whatever's happening over here is a mirror image of what's happening over there. And I believe this P is the distance to the, I'm kind of thinking of like a parabola, you know what I mean? Like with a parabola, P is that distance right there,
Right.
you know? And because the eccentricity is 1, then this distance equals that distance, right? For parabolas, it's always 1. But for something like an ellipse, you can see how the eccentricity is different. The distance to the focus is different from the distance to the directrix. Although in this picture, you can hardly tell, right?
Right.
Because the eccentricity is small, between 0 and 1, then it should be, this distance should be smaller than that distance right there.
Right. By
Right.
3/4, right?
Yeah, exactly. So if I took this distance divided by that distance, then that should be 3/4.
So if one's 1, the other one would be 3/4.
Right. So since this one is 1, right? If this distance is 1, then this distance right here, call it x, would not be 3/4.
No, it'll be 4/3.
Yeah. Which makes sense, because again, that's supposed to be shorter than that.
Right. Oh, okay. Yeah, okay.
Right. Yeah, so that's the distance to the directrix. Yeah. And And this reference here in the book doesn't seem to indicate the orientation of it. It just tells you what shape it is. It's given by this, graphing a conic section. So they still plot a few points. So basically when they're graphing a conic section such as this one, they're still plotting a few points, but you're plotting the points with the foreknowledge that it's going to be an ellipse. So that does make it a little easier. You only need a couple points. And if you know it's going to be an ellipse, you know how to connect them, right? So for example, if theta equals 0, right? If theta equals 0, then the sign of 0 is 0, you end up with a negative 3/4 for r. But if theta equals pi over 2, let's say, then the sign of pi over 2 would be 1.
1. -1.
So that would be negative 1 bottom, so negative 3. It's going to be a weird one because all the radii are going to be negative, right?
Right.
At pi, this goes back to 0, so it's going to be back to negative 3/4. And then at 3 pi over 2,
We go back
Positive
to
3.
because that's going to be a negative 1, right? So it's
Oh.
going to become a negative 7 at the bottom.
Yeah.
So negative 3/7, right? A little smaller. So I think I can come up with a better graph than this. I should be able to gather the orientation of it now. You can see now that the graph should look something like if theta equals 0, that is to say in the direction of the positive x-axis, the radius is actually negative 3/4. So if this is negative 1, then this would be a point on the graph, right?
Right.
And as I sweep through the first quadrant, it looks like the radii are actually going to be negative, right? And when I get up to the positive y-axis, it's going to be a negative 3/4. Oh no, sorry, negative 3 actually. So 1, 2, 3. This is going to be a point on my ellipse. And when I swing through the second quadrant, end up at the negative x-axis, I'd actually have a negative 3/4, so I'm starting to see some symmetry here, right? As I sweep through.
Hold on, so. It's, you went from pi over 2,
Yep.
and then to pi.
Mm-hmm.
Okay, because
Yeah.
now it's a vector, so it goes back the opposite way type thing.
And there's a lot of points I could be plotting points along the way,
Mhm.
but I'm purposely being really rough, skipping past them, just to save time, because I know there's going to be an ellipse,
Okay.
so. Yeah, but if I didn't know it was going to be an ellipse, I'd probably want to plot the points along the way as well, so that I can connect the dots and see what it's going to be. Yeah.
And then 3/7 is.
Yeah, 3/7, negative 3/7. So it's going to be up here, and actually 3/7 is smaller than 3/4, so it's actually going to be, not even halfway to 1. I guess about right here maybe.
So it really flares out as it gets closer to the.
Yeah. Yeah, if I just had these 4 points alone, I wouldn't necessarily know that that's an ellipse. But if it is an ellipse, it looks like it's going to have this. It's going to have to bulge out a little bit further to get up to here. Right? And if indeed the distance to the focus is 1, right? Then I think my foci would be over here at 0, -2. I just added 1 to that.
-4/7?
Yeah, that's actually 3/7 minus 1, so yeah, -4/7.
0, -4/7, sorry.
Yeah.
But then the directrix would be
Mm-hmm.
at +4/7?
Well, let's see here. That's 4/3, right? That's 1 1/3.
Mhm.
So there'd be 1 over here at y equaling 3. 1 1/3 puts you at 4 1/3 as a mixed fraction. And then up here at y equaling whatever, 3/7 plus 4/3 is
21, well, 21 on the bottom. That's
Yeah. 9 and 28.
9 and 28. 9 and
9 and
28.
17, 37.
9 and 28. No, 9 and 28? Yeah, 37. Sorry.
Yeah. Up there.
Which then reduces to what? Like freaking 1 in
Yeah.
16 over 21?
Yeah, so yeah. 16, 21. Yeah, interesting. And you know, we could do, if with some more work, we could figure out where the center of the ellipse is. We could find the length of the semi-major axis, the length of the semi-minor axis.
They can actually write an equation for that, right?
Yeah. Exactly. So yeah, so there's a lot of pieces to the puzzle coming together with this stuff. But again, I'm not holding you to this polar stuff, but you know, with more time, another week, you know, we could handle that, right? Yeah, and I guess it wouldn't be that bad, because all you'd have to do is include in your notes, if you have room for it, right? Is just this little box, right? That one I had to refer to, just know what to do. This one right there, right? So that was pretty useful, right? But you know, even if, now I'm just kind of, you know, tangenty, but like, notice that like, if I didn't have that box, you know what I mean? And if you feel a lot more comfortable with rectangular coordinates, an alternative solution would be just to write this in rectangular coordinates, right?
Change theta to x.
Yeah, exactly. Like notice, I could actually just say that r times -4 plus 3 sine theta. This is like another way to do the same thing. So -4r plus 3r sine theta equals 3. I put it in this form because I know that r sine theta is x, no y. So in other words, if I write it like this, 3y, how do I want to write this actually? You can say that. Which means I'm just squaring both sides. Why? Because I know that x squared plus y squared equals y squared. Right. And at this point, yeah, I guess I'm gonna have to distribute. But I can now see that I have 16x squared plus 16y squared equals 9 minus 18y plus 9y squared. So 16x squared, right?
Mm-hmm.
Subtract the 9 from 16, I guess that'd be 7.
I can do that. I can do that. Wait. Plus 18. Yes.
Yeah, I'm just gonna say equals 9. But yeah, at this point, it's starting to look like something familiar, something that we have been talking about, right? It almost, and in fact, I think with some more work of completing the square, I did this once, but it wouldn't hurt to do it one more time. This is probably more relevant to the test right here.
Here we go.
Right? You can see how, in this case, I can see that 16x squared, if I want to complete the square, see this first one is already a perfect square right here.
Right.
It's these two y's, I want to combine them, right? And I can do that by completing a square, by saying 7 times y squared plus 18/7 y plus something that'll make it a perfect square.
Oh, yes, I know what this one is.
I don't.
So, to make a perfect square, he told us on Monday, it's generalities, it's x squared plus 2ax plus a squared. So, a squared is a, or in this case, 18/7 divided by 2.
Mhm.
So, 36/7.
Divided by 2, not
Divided.
multiplied by 2,
But then,
18/14.
right?
yeah.
So to divide this by 2, you get 9/7.
Oh, yeah, because you gotta flip, yeah, my bad.
And then you square it, so you get,
81/49.
yeah.
Hey, mister, I wasn't here last week, I got this.
I catch on quick.
Yeah, and that makes it a perfect square, but of course I can't just arbitrarily introduce a term on the left-hand side, right? It would no longer be an equation anymore. So what exactly did I just add to the left-hand side?
81/49 walls times 7.
Mm-hmm. So I actually just added 7 times 81/49 to the left-hand side. So I need to add the same thing to the right-hand side. So now everything is in equilibrium again. The left-hand side is still equal to the right-hand side. And that's a perfect square. As long as you do what we just did, take half of this and square it and put it right there.
I'm sorry, take half of which one?
The second coefficient.
Take half of that and square it,
Yep.
and that's gonna be that
Mm-hmm.
term with no variable.
Yep.
Excuse me.
Mm-hmm. 12, 14, 1. Oh, that's nice. That's a perfect square. At least the numerator is. And so I have in the back of my mind, it's not written on the board, but I have in the back of my mind the general formula, the general form for these conic sections in rectangular coordinates. I have in mind things like, where did they go? Things like these, right? This is the hyperbola. Notice how it equals 1. Or up here when you had a ellipse, see how it was equal to 1, it just had pluses instead of minuses?
Mm-hmm.
And this is starting to look like one of like those. Because of the plus, I'm thinking ellipse, right? And if I make this the right-hand side into a 1, I'm going to divide both sides by this fraction, right? Or maybe you might prefer to think of it as multiplication by 7 1/44. Either way.
Yeah.
So if I multiply both sides by 7 1/44, so I'm going to get, what is that, 7 over 1/44 times 16x squared plus 7 over 1/44 times 7y plus 9/7 squared equals 1. I'm trying to put it into this form where where I can clearly see what A and B are, right? And I can see now that is, well, let's see. One of these works out nice, one of them doesn't. Go in evenly into 144? Does 4 go into 12? It does. I think it goes in 9 times. So 16 goes over 144 is, 16 goes over 144 9 times. So I get 7/9. So I'm gonna put so multiplication by 7/9 is the same thing as division by 9/7. And likewise, here I have 47 squared over 12 squared. Multiplication by 7 squared over 12 squared is the same thing as division by 12 squared over 7 squared. All right. Or 144 or 49. But the nice thing about that is I can see it. I can almost see what A and B are. A is the thing that you would square to get 9/7. In other words,
3 square root 7.
That's supposed to be a 1 on the right side of the equation though, right?
yeah, it is. Next. And at this point, I can clearly see that this is an ellipse. The center at 0, negative 9/7. The distance along the x-axis, right, is 3 over square root 7, whatever that is. That's a decimal. And the distance along the y-axis is going to be 12/7. So I would start here and add 12/7, subtract 12/7 to find the top and the bottom of this ellipse. I would add and subtract 3 root 7 from 0 to find both sides of the ellipse, just kind of connect the dots. And that's kind of, maybe I erased the picture too soon, but I think that should correspond perfectly with what the conclusion we reached doing it with polar coordinates. So.
Maybe I was writing as you said.
Mm-hmm.
The center is at 0, 9/7, negative 9/7.
That's right.
Because it's on the y.
Mm-hmm. Yeah, because you think of this as being x minus 0 squared and y minus negative 9/7 squared. So you can see how the center is reading off
H and K, yeah.
H and K. From these, you can figure out what C is. Right? C is the distance to the foci. Right?
Which should then be what we found earlier.
Well, it's not exactly P, because remember C is the distance from the center to the focus.
Right.
P was the distance from the edge of the
Directrix.
edge of it, from the vertex. I don't know if I'm not sure if I can call it a vertex. You know, the vertex to the focus.
Mm.
You know what I mean? So in other words, so we had like this ellipse looks like this with foci here and here. The center's there.
Right.
So the distance from the center to the focus, that's C. The distance from here to the edge of the ellipse, that's P.
Oh, that's what I was saying. So, but they should meet up. Right?
Yeah. Whereas the total distance, that, like in this case, it's 12/7. Right? So, interesting stuff. Conic sections. So I think if you were like completely comfortable with polar coordinates and you had access to that equation, it might be a little quicker. I think it was nice that we could recognize immediately that it was an ellipse, you know, just based on the once you could identify the eccentricity.
Mm-hmm.
This one has a little bit more work on the front end in that you have to put it into rectangular coordinates and then complete the square, and that's no small amount of work. But once you get there, now it's pretty clear the geometry of the ellipse as well.